All right, we are looking at Unit 10A, the fundamentals of geometry, and a lot of this is probably something you've heard, but then some of it will be, an extension of what you've heard in the past. So a lot of the formulas I'm sure you've seen before, but some of the terminology may be a little bit different as we expand on some of these ideas and where some of these things came from in geometry. Okay, so the beginning is just something interesting. The word geometry literally means earth measure, and you can read a little bit about the ancient cultures, but geometry was always more than just a practical science, because it's something that was tangible, it was hands-on, we could see, we could measure, and it's been something fundamental for a very long time in our history. There was a Greek mathematician, his name was Euclid, and he summarized the Greek knowledge of geometry in a book called Elements. It's very difficult to read, but that's where a lot of what we have today kind of stems from. And the geometry described by Euclid's work is called Euclidean geometry. And Euclidean geometry is the familiar geometry of lines, angles, and planes. And it's not airplanes, but planes such as this picture right down here in your bottom right. Okay, so in this unit we're going to be exploring the foundations of this idea of Euclidean geometry. Okay, now geometric objects such as a point, a line, or plane, they represent idealizations that do not exist necessarily in the real world. So like a point, we don't walk around and there's points all over. There's not infinitely extended lines that we can point out, but we describe them, we give them definitions, and then we're able to expand upon those. So in a geometric point actually has zero size, and so there's no size to it, there's no dimensions to it, but many real phenomena approximate geometric points. Stars, for example, appear to our eyes as a point of light in the night sky. So these things, again, can be applied in kind of a basic sense. Now, a geometric line is formed by connecting 2 points along the shortest possible path. A line technically has infinite length and no thickness. Now, because no physical object is infinite in length, we usually work with what we call line segments, so portions of lines or piece of a line. So, wire is a good approximation of a line segment. And then the geometric plane is a perfectly flat surface that is infinite in length and width, but it does not have any thickness. So when you think of a plane, you might think of like a piece of paper, but a piece of paper that's infinitely large is what we're talking about, and again, no thickness to it. So again, these ideas are rather difficult to think of on the surface, but just gives you an idea. So a smooth tabletop is a good example to a portion of a plane, and so when we talk about these objects, we can think of them in as far as dimensions. So the dimension of an object can be thought of as the number of independent directions in which you could move along that object if you were on that. So if you're a prisoner confined to a point, you would have no place to go. You couldn't move at all. So a point has 0 dimensions. A line has 1 dimension, is one-dimensional, or 1D, because if you walk the line, you can move only in one direction. Technically, forward and backwards are the same direction. One is positive, the other is negative, but you can only move in one single dimension. Now, in a plane, you can move in 2 independent directions, such as north, south, east, and west. And all other directions are a combination of the 2 independent directions. So you can go northeast, southwest, or whatever the case may be. But the plane is, again, is a 2-dimensional or 2D object. In 3-dimensional space, such as the world around us, you can move in 3 independent directions, north, south, east, and west, and then up and down. So we add that next element of up and down to get into 3 dimensions. So when we talk about dimensions, we can also think about dimensions in terms of the number of coordinates required to locate that point. So if we come down here, a line is one-dimensional because it requires only one coordinate, such as x. So here's our line right here. Only requires one coordinate to determine where you're at on the line. And two-dimensional object requires 2 points. So you have to have you can think of it as x and y, or in this case, going to the east and then going to the north, or however you view that. And then 3 dimensions, you need 3 points to determine where you're at. And it's hard to see this in a 2-dimensional drawing, but you've got to go some direction, say in the east, you've got to go some direction north and south, and then you have to go also up and down. So that takes 3 dimensions to identify a point or locate a point. And in 3 dimensions drawn on a 2-dimensional surface such as this, it's really hard to visualize, but technology has really brought this to life where you can actually rotate these graphs around. But you will not be asked to graph things and draw things in 3 dimension on a 2-dimensional surface. For that one, stay tuned for like Calculus 2 is when you'll actually have to do things of that element. Okay, let's look at dimensions here. So if you were to examine a closed book, so imagine you had any book and it's closed, seen in front of you, how many dimensions are needed to describe the book? Okay, if you think about the book, you've got the surface of the book. So if we're looking at the front cover of the book, you have kind of a plane surface that's 2-dimensional, and then you've got a thickness. So this is going to be 3 dimensions or 3D again, because you look at it as kind of a length, a width, and a height. So you have 3 dimensions. And how many dimensions describe the surface or just the cover of the book? So if you're only looking at the surface, if that's the only thing you're fixated on, then that would be 2 dimensions. You would just look at the length and the width, but you wouldn't look at how tall the book is. You're just looking right at the cover itself. Okay, how many dimensions describe the edge of the book? So if you're looking along the edge, so you're just looking right along, say this is the cover, and you're looking just at the side, it would look like a line. So you're not worried about the thickness of the book, how tall it is, you're looking just right at that edge. That would be 1-dimensional. And then, how could we describe some aspect of the book that represents 0 dimensions or a point? And one way that I think of a single point is if you were to kind of fixate or look at a corner of the cover or corner of a page. Either one of those, if you were to fixate just on the corner of a single page or just on the corner of the book, you would basically be looking at a single point on that book. So that would be a way to describe 0 dimensions when you're looking again, we're looking at a closed book. Just checking my time there. So that's a little bit about dimensions. Now we're going to look at another portion of geometry, which is angles. Okay, hopefully again, angles is something that isn't new to you, but we're going to talk just a little bit about these angles here. So the intersection of 2 lines or 2 line segments is what forms an angle. The intersection of those points is called the vertex. So if we're looking at this, where to go here? Just lost my place. Figure 10.3 shows an arbitrary angle at some point A where you've got a couple of line segments that come together, and when they come together they create that angle right there, that angle A. So that's how you would define an angle. The most common way to measure angles is in degrees. You can also measure in what's called radians, but degrees are derived from the ancient base 60 numeral system by the Babylonians. You'd have to do a little bit of history research on that, but Babylonian number systems are in base 60. Something that's kind of base 60 is our minutes and our seconds. That just means once you hit 59 seconds, then we don't say 60 seconds, we convert that to 1 minute, but that's what it means by base 60. Now, by definition, a full circle encompasses 360 degrees, so an angle of 1 degree represents 1/360th of a circle. Okay, now to measure an angle, we imagine its vertex as the center of the circle. So if the vertex is the center of the circle, then we say, if we were to draw a line from some arbitrary point to that center and then back out, then that angle A would be kind of a measure of a portion of the circle there. So we say in this case angle A subtends, and it says 1/12 of the circle, and what that means, if that angle is 30 degrees, 1/12 times 360 is 30. And so if we want to find out, for example, in this problem right here, the angles of the circle, find the degree measure of the angle that subtends each of the following parts. So if you have 1/5 of the circle, so you'd say I've got 1/5 of my circle, so an angle that subtends or kind of cuts through 1/5 of the circle, and then you times that by, there are 360 degrees for every one circle. Your circles will cancel, so you'll get 360 over 5 degrees, or 72 degrees. So 1/5 of the circle, that angle is going to be at 72 degrees. If you're 5/6 of the circle, hopefully you can say, well, if I'm 5/6 of the circle, that's going to be much bigger than 72 degrees. Follow the same idea. If I've got 5/6 of the circle, got an angle that covers 5/6 of that circle, then I'm going to times it by 360 degrees, degrees, for every one circle. And again, circles will cancel, so you'll get 5/6 times 360, and this is in degrees. And if you take 5/6, multiply it by 360, that will be 300 degrees. So 5/6 of the circle, you're going to have an angle measurement of 360 degrees. So that's how we can identify angles that are either 1/12 or 1/5 or 5/6 of a circle, and we can precisely get that down to exactly how many degrees is needed in order to I keep using the word subtend, but to measure that portion of that circle. And so if you have any questions on this, please don't hesitate to let me know, and in the next video we'll pick up on plane geometry.